Here's Bartlett from USC, and he's talking about something. Let's see. Detecting object boundaries in natural scenes requires incitatory cell-cell interactions.
Well, I would thank the organizers, but I am one. Okay, I'm going to be talking about the work of Gabriel Mel, Chait Ramachandra, who began, well, maybe graduated 5 years ago or so. Gabriel's been kind of taking the lead on this. Yes, we're related. Actually, Gabriel, where are you? Gabriel is, he's hiding. Well, Gabriel is now a graduate student at Stanford in neuroscience, and some of his professors are here. And I think he drove up to make sure that I would give him full credit for this. I'm going to try to steal it. Okay. And actually, as a human interest story, my father is also here, so Gabriel's grandfather, emeritus professor of biophysics. And my sister even came down here. So this is, I was saying I felt like I was a kid at a track meet, and the whole family came to, you know, kind of cheer you on. Okay, so Ken made a comment yesterday about two kinds of people and two kinds of projects among people who like to use models. One of them being the type who take complicated data sets and try to sort them out, confusing, incompatible, paradoxical results, and build a simple model that's parsimonious that explains the data. And then the other type being ones where who are willing to kind of make fools of themselves and try to suppose what a neural circuit is doing, and then study the task that neuron is, or that circuit is facing in the world, to try to understand what the task is, how to solve it, what the difficulties are, and how you might engineer a solution to that task using pieces that look like what the brain has available, and thus try to build a system that might be isomorphic, you hope, to the actual neural system. And then you could, maybe make correspondences. So this is a talk that's definitely in that second vein. So I'm going to, the difference to a traditional sort of talk is that I'm going to spend, kind of like Bruno did, a lot of time talking about the problem. And we spent a long time studying this problem faced by the nervous system in order to try to get ideas about how to solve the problem. So this has to do with, well, object recognition is sort of the high-level thing. If I say to you, what is this object here, what would you say?
Line.
Good, nice job. And this one? Good. So how do you know that's a gorilla?
He's got his paws on the ground.
Well, I didn't mean how did you know it's not a macaque. I'm just saying the way that we answered this question, and the reason that artists draw these kinds of pictures, is that the key information for object recognition, for this kind of classification problem, is sort of lies in the boundaries of the objects, the contours that describe the object. I've got a nice demonstration from Irv Biederman. Maybe some of you have seen this before. So I'm going to start a little movie here, and then I want you to tell me when you see a fire hydrant. Oops. Okay. Fire hydrant. Good. You guys are good. Okay, so let me stop this thing. Now, that is an illustration of the fact of the power of contours to evoke the object category inside your brain. And so contours, what are contours? Contours are really orientations at positions. That's what the information contained in contours is. And so since we're so good at object recognition, it is pleasing to discover, and it wasn't us who discovered it, it was Hubel and Wiesel who discovered this back in the early 60s, that the first processing stage in the visual cortex seems to report the position and orientation of object boundaries. We've seen already, in a couple of talks, the cells in V1 we all know are tuned to orientation, of course, in position. So they would have a receptive field looking for, say, bright here and dark here and unoriented axis. And so this might be, and Hubel and Wiesel certainly said it, and umpteen other people have said it since, that these would be the elements that would be the first level of computation of the contours that would eventually let us recognize objects. Now, one of the quandaries that you run into almost immediately is that if you take a conventional model of a simple cell, it's actually a very poor boundary detector in natural images. I'm going to show you that quantitatively later, but we made this slide last night actually to kind of illustrate this. A conventional model of a simple cell is that you have kind of a linear filter with positive coefficients and negative coefficients. So that would be like this, basically. That's kind of what that is intended to signify. And then that thing goes into some kind of divisive normalization. So really, from a simple point of view, you could think of this as sort of adding up the top row minus the bottom row, the pixel values, and then dividing by the top plus the bottom. It's kind of a surrogate for a simple cell model. Now, the problem with this is that if you applied this operation, this filter and this divisive normalization, to these three pictures, you would get the identical result. And I think you'll agree, this is really a high probability contour, and then who knows what this even is. And this doesn't look like a contour at all, and yet they yield the same response in a simple cell model. So a simple cell is not a good discriminator of shape. And this is frustrating because that's what it's supposed to be doing. So this leads us to the problem, well, what exactly do you need to do in a natural image? Well, these aren't natural images. This is a toy demonstration. Nonetheless, I think kind of striking. But what do you need to do in a natural image in order to decide whether there's a boundary of an object at a given location? What does the actual problem look like? So we came at this problem with great vigor to try to figure this out. So if I were to show you this picture and ask you if there's a contour running through this, what we call a reference location, this dash box kind of in one end and out the other, would you say yes? I think you would agree there is. And here you would say no. And so if you wanted a computer program or a brain to answer this question automatically, or to see the contours that are there and not see the ones that are not there, what does the computation look like? Now, you shouldn't feel that the brain or any machine that would be trying to solve this problem is limited to having one kind of simple cell-like receptive field overlapping with the location where you're asking the question, and you can only rely on that one value. We know that in the cortex, in a small area, there would be perhaps hundreds or thousands of cells whose receptive fields overlap with the position of that location where you want to know the answer. And why can't you take advantage of all of them somehow? Why should you not be able to do that? And maybe you could perform have a much better shape discriminator than you could with any individual cell. And so what we did was we asked, well, we basically used Bayes' rule to tell us how we would use all of the filters in the neighborhood of a place where we want to know whether there's a boundary. What would Bayes' rules tell us is the way to combine the information from all of these nearby cells in order to get the answer. So the probability that yes, there's a boundary, given simple cell 1, simple cell 2, simple cell 3, these guys just all over covering the neighborhood, and there could be hundreds of these. And so this is basically a rewrite of Bayes' rule. And I'll point out the form of this. It's in a form where it says it's 1 over 1 plus e to the something or other, and that's a sigmoid. And the something or other is a sum of terms. And so a thing that can compute a sigmoid on top of a sum of things, well, that's what people think a conventional neuron model in a neural network is. You add a bunch of things up, and then you run it through a sigmoid. So that's the form of this calculation under the assumption. There's an assumption here, which if it bothers any of you, we can come back to it later. So the question is, what is it that you should be adding up and putting into a sigmoid in order to solve this problem according to Bayes' rule? So here's a neuron that has a receptive field that is sort of the one that's right overlapping with where we're asking the question. Here's a neuron whose receptive field is sort of off to the side and up and misoriented, and here's another one. And the point is that the things that we should be adding up, when this neuron fires, his firing rate should go through this function. This is a function of his firing rate. And the function could look something like this. As this firing rate increases, then what you want to add up is this value as a function of f1. And here's a value as a function of f2. And here's a thing as a function of f3. That's a cartoon of what these things look like. Now, which is a little bit weird, because normally when we think of a cell affecting another cell that's trying to decide if there's a boundary and it's adding something up, we usually think of the cell attaching through, let's say, an excitatory connection, in which case this guy's firing rate, as it increases, would increasingly excite a cell like that, and then the function would just be going up and continue to go up, or inhibiting and it might go down and continue to go down. So what are these funny looking functions that we're ending up with? Well, the nice thing about natural images is that we can go to them and collect this data, which is to say, what does filter 1 do when there is a boundary, and what does filter 1 do when there's not a boundary, and filter 2 and filter 3. Collect the data and actually evaluate these functions and see what messages these simple cells should be sending to a boundary cell. Or that was the goal. And here's an example of collecting that data. So this is some filter which has got an orientation that would be centered here at the question place, the reference location, but a little bit off-oriented. And if we collect the value of that filter applied in many, many natural images, thousands of natural images, where there are boundaries crossing through here, that's the red data, and where there are no boundaries, that's the blue data. Clearly they're different, which means this cell responds differently when there's a boundary and not a boundary, which is good, meaning it can help tell whether there's a boundary or not. And so that's these likelihood functions on and off boundaries for this cell. And we can do the same thing for oh, by the way, when this cell when there is a boundary here, this cell tends to have a value that's away from 0. It has a positive value. Why? Well, it's kind of aligned with the boundary, and so it will be overlapping with it and get stimulated by it. Whereas when there is no boundary, its responses are much closer to 0 on average. This cell, which is exactly misoriented for the boundary, when there is a boundary, this cell tends to respond almost 0, so it's very close to around 0. Why? Because it's not being activated well by a horizontal boundary.
How is phase playing in here? Like, I mean, that guy could be positive or negative depending on the phase of the boundary.
Thank you for asking that. What this is, this picture literally tells you the value of that filter moving to the right of the origin, and if you were to flip the polarity, you'd be moving to the left of the origin. So that's the.
So you're considering boundaries with a polarity. And
yes. These are polarized, as you can see. This is sort of the light-dark boundary, but then.
Not only the filters, but also your boundaries that you, in your images, have a label of polarity. Otherwise, you couldn't do that.
Yes, they do. Well, every boundary has a polarity, so there's no loss.
You know the polarity. That's the point.
Well, you don't know. I mean, you know the polarity by the polarity comes out of this.
Okay, so you just take the absolute value.
Yeah.
So Bartlett,
Yes.
the original problem you posed was, is there a boundary or not?
Yes.
And that looks like you're asking, is there a boundary for particular orientation?
Well, the way that we pose the problem, you could pose, is there a boundary somewhere in the world? Or we can say, is there a boundary running through this box? That's the question that we're asking.
So now you're looking at boundary in a particular direction.
Correct. In other words, because you think of a simple cell that has an orientation as being sort of a dumb way to get some evidence about whether there's a boundary at that location, at that orientation. Yes, a simple cell is an orientation.
Simple cells, I mean.
Well, so the way that we asked the question was the way that you would think to ask it if you thought a simple cell was doing boundary detection, and that it would be detecting a boundary at a location of its location and its orientation. So we have the question is oriented.
And its phase.
Yes.
And are you varying contrast when you do this?
Excuse me?
Are you varying contrast?
Okay, so this data set that you're looking at here is sort of, you can think of it as an isonormalized data set, as if there's a divisive normalization algorithm that is operating in the background. So that's to sort of simplify the picture. Let me just show you, I mean, this is only to say that we can collect the data at all orientations, and then at different sort of shifts up above the place of interest, this reference location, and we just get a bunch of different data here. Oh, and now I wanted to go back here, and I'll just say, remember that the thing that we wanted, these are the likelihoods. We want those colored terms 2 slides ago that we were trying to evaluate, those funny-looking functions, are gotten by taking the ratio of the red to the blue, meaning places where the response when you're on a boundary tends to be larger than the response when you're off a boundary. If you see a large response, you figure, I'm probably on a boundary. That's the way that information can be helpful. If you take the ratio of those 2 curves and you take the log of that, now you end up with these log likelihood ratios, and I have to move through these animations again, and you get these functions. So if we go back to this one where we had the red and the blue, what this says is, as this filter's value goes up, then the evidence for there being a boundary that it should send to the boundary cell is just ever more positive as its value goes up. Now, this cell over here, as its value becomes more and more positive, then its evidence that it sends to the boundary cell should be ever more negative. In other words, inhibitory purely. But there are many cells such as this one here, which has a kind of a mixed sort of evidence where at first up to a certain value of firing, of its firing rate essentially, it sort of sends positive evidence, and then if it starts to fire even more, it starts to turn around and become negative evidence. Here's another great example of that. So we have a lot of these non-monotonic, essentially functional interconnections between the simple cell precursor and this putative boundary cell that would be listening to the simple cell. And so this kind of thing looks like it's excitatory. This kind of thing looks like it's inhibitory. But these things look like they're mixed. And if you're wondering what incitatory meant, it was supposed to represent a mixture of that. Now here's the whole data set that we collected. And you can see that this is now, we just sort of added shifts, horizontal shifts, and grouped them together in groups of 5. And so you can see there's there's a spectrum of interactions that are called for by this, if you want to solve this problem using simple cells as the inputs. And you know, it's got some well, I don't want to say, it's got some non-trivial interactions between the cells that are being asked for, but they still fall into a family of things that kind of range from things that go up monotonically or go down monotonically or have an upside down U shape. That's what we saw. Now, how do you get, okay, it's easy to see how you get excitation. You just send some excitatory synapses over to the guy. It's easy to see how you get inhibition. How do you get these non-monotonic effects where one neuron, you kind of excite a guy more and more, but as you fire more, you start inhibiting him? It's a little bit like length tuning or some of these other non-monotonicities that you get in the cortex. So we thought that the most obvious candidate for the local circuit motif that could allow you to do all of these types of interactions is this one. This comes from Massimo's paper. And it's basically that whenever you're in the cortex and you look at one cell and then you look at how it affects another cell, it's almost always the case that it both directly excites it and that it inhibits it indirectly through an inhibitory interneuron or two, or, you know, and there's more complicated versions of this circuit. But this type of, if you imagine that the excitation, depending on which one is more powerful, which of these, you know, how the parameters of the circuit are tailored, that you could get pure excitatory effects, pure inhibitory effects, or effects where the excitation kicks in at first and then the inhibition overwhelms it and turns the effect around. Okay, so that's something that this type of circuit we hypothesized could produce. And here's just another way of saying it, that you could have a pure excitatory effect on a downstream cell. You can have a pure inhibitory effect where you just hit an interneuron and you send no direct excitation. Or you could have this mixed incitatory kind of effect by both exciting and inhibiting simultaneously. So we asked, well, okay, you know, if we just did a simple conceptual model for increasing the effect of the excitation with one curve and increasing the inhibition with another curve, could we reproduce this type of data? And the answer is yes. Here, let me show you the actual thing. So, you know, for this type of, okay, now I'm out. Let's see. Okay, this kind of works. So like this guy here is what you have from this excitatory curve that turns up and then the inhibitory curve kicks on later, and that's what brings you up and then back down again. So by kind of very, very simple conceptual model, having an excitatory sigmoid and then an inhibitory sigmoid and just adding them together, you can already, you know, in this kind of very abstract incitation scenario, you can represent the entire spectrum of these cell-cell interactions that we measured, including the non-monotonic ones, which is pleasing. But if you look at the sigmoids, you know, that we kind of collected them all together here. And by the way, it doesn't matter at all almost how you choose the parameters of these kinds of sigmoids. This type of fitting works very, very easily. But no matter how you do it, you're going to find you have a variety of excitatory sigmoids, the different scale, the different threshold, may differ in gain. So somehow you have to account for, well, how are you going to get all of these different sigmoids just conveniently there where you need them in order to achieve these sort of tailored effects? And you know, what sigmoid do you need? And so can we leave the dirty work of sort of creating these interactions as needed, but to a learning rule, rather than having us just come up with a corny, you know, hand-waving simple model? So the answer to that question is yes. A learning rule can do the dirty work. And what we have here is here's some simple cell presynaptic partner that's communicating to a boundary cell. And all that we did here was we simply made a bunch of variations of it with different different output nonlinearity. So they all have the same receptive field, but some have different thresholds, and some have different gains. So we kind of represented the natural diversity that you would expect among a population of actual neurons. And we did the same for each surrounding neighbor. So just imagine there's a small population of simple cells covering every location with varying thresholds, gains, and so on. And then we used a one-layer learning rule. This is no deep network. It is a one-layer learning rule where the coefficients were learned onto an inhibitory interneuron, which summed up all the inhibitory effects. But these are plastic weights, and then these are plastic weights onto the boundary cell. And just use the one-layer delta rule to train with our edge boundary data that a stimulus, a picture that would come in and activate all these filters either was or was not a boundary, and that would train this neuron, and these weights would be learned. What got learned? So these colored curves are what got learned, and they might at first glance look reminiscent of the curves that we just simply got by measuring, collecting data from images, human labeled, dividing histograms, and producing log likelihood ratios. What was learned in the sense that the way that this cell influenced the boundary cell, we teased apart the independent effect of this one cell was these curves, which look reminiscent to the ones that Bayes' rule told you should collect. And in fact, the dashed line is the one that was on the previous slide that was the one that Bayes' rule told you that you should collect, assuming independence.
In this case, you were learning just on a binary yes, no. Is there a boundary there?
Yes. So it's a really simple learning situation. But in many cases, what got learned, these interactions got learned were what the optimization to do a good job at distinguishing the boundaries chose a slightly different curve than maybe what the Bayes rule said. But we expected that because these filters are not actually independent of each other, which was an assumption that Bayes rule makes. And so we would expect that the learning rule would try to compensate for the non-independence of the different filters in choosing how they would affect, how these connections would be, how they would be learned. So anyway, so basically the point is it's a trivial learning problem. I'm almost done. But the other nice thing about this kind of approach, which I value, is that we can, we made this little model that says, okay, we have this circuit I showed you a couple slides ago, and it's a bunch of connections and they're learned. How well does it actually do to solve the problem that we said we were trying to solve? So how well does it detect boundaries, this detector? So this is kind of a fun graph to look at. A good way to quantify how well you do in a classification task, especially when you have rare targets. So edges and boundaries are very rare in natural images. So if you just said no all the time, you'd be right like 98% of the time. And you wouldn't want to just say, oh, I'm right 98% of the time, because 100% of the time you say, no, I don't see a boundary. That would be dumb. So you trade off recall, which is how many of the actual boundaries that are shown to the classifier are caught and are classified as, yes, they're boundaries. That's where you want to be. You want to catch 100% of them. And then when you say, yeah, I see a boundary here, you want to be right 100% of the time. You don't want to say, yeah, there's a boundary, and then 80% of the time it isn't. So you want to be up here at 100% precision. So this is where you would really like to be. This is what a simple cell, like the generic model of a simple cell that's a linear filter with a normalization, does. And it's very far away from this corner. The rest of these curves are just different variations of these simple learning models with like 10 simple cell variants, like the one I showed you on the previous slide is this purple curve. But you could make 100 variants of the cell. It doesn't improve anything. So, but anyway, if we look at the performance increase, this is, if we just pick a number like 80% recall, then a single simple cell will have precision about 30%. It means that 70% of the time a simple cell says, yeah, there's a boundary here. There isn't. And whereas this combination of where the boundary cell gets to listen to a bunch of simple cells through these incitatory local circuits, the precision is significantly increased. I mean, it's still not perfect by any means, but this is still a very simple model. But anyway, it's significantly increased from something like 25 or 6% or something up to around 50% precision. So there's a definite gain made by exploiting this type of circuit, local circuit motif. So here's what we did, just to remind you. We assumed, this is the assumption, that we kind of go out on a limb and say we believe that there are boundary detecting cells in V1. We assumed that they receive input from conventional simple cells. that's also an assumption. Then we collected contour statistics and asked Bayes' rule to tell us how these dumb cells should influence the smart cells, what the interaction function should be. We found that the interactions have a spectrum of cases ranging from pure excitation, pure inhibition, to these non-monotonic effects. We showed that the entire set of those effects can be produced by this incitatory circuit motif, which is known to exist in V1. And then we showed that, that those parameters can be easily learned with the simplest type of learning architecture that you can conceive of. And we showed that it improved the performance significantly over not doing it, basically. So I would conclude by saying, we can't, one is tempted to generalize from what we learned, but the fact is that that circuit motif, which is all over the cortex, allows for the functional interactions between cells to be much richer, not to be limited to the way that we think about conventional neural networks as having excitatory and inhibitory interconnections between units. But it's quite useful to think about the connections between units as needing to have higher dimensionality and be actual functions of activity level as opposed to just scalars of times an activity level. And so we think that it's possible that it's not just in contour detection that these types of non-monotonic and this variety of interactions is needed, but probably in many difficult discrimination tasks. We have reason to believe that that would be the same type of computation that would be needed. And so it's worth keeping in mind that we maybe want to generalize the idea of a synaptic weight to the idea of an incitatory family of interaction functions that are possible. Final comment, I would say, we're talking about like what. Now, let's say we blundered on the right solution, and this is really what the connections between cell pair, these are the cell pair specific connections in the cortex we are predicting should have these very specific forms. And let's say it's accidentally correct because we got lucky and we nailed it. I think if you look at this, you can kind of get the sense of how difficult it would be to figure this out if you didn't come at it by assuming the task. I mean, if you actually went and started measuring things and then you'd say, oh yeah, there's some excitation inhibition, it would be really, really hard to collect enough data. And then if you did collect it, you wouldn't really know what it meant necessarily. So this is we think this gives us a feeling of security to come at it with an expectation based on assuming what the task is. And that it would be difficult to do it if you weren't willing to assume what the task was. Oh, well, that's it. So, thank you.
Time for questions. Why don't you pick?
Right.
Now your learning rule is basically a supervised learning rule, which uses a signal that's not available. Do you have any ideas how to turn this unsupervised?
Yes, we do have ideas about how you could have unsupervised, but yes, that is an unexplained aspect of this. But there are many ways very inexpensive ways of getting boundaries from motion and so on that we think could provide the supervision, but we did not show that. But I have faith that could work. Hannah.
So I have two questions. So first, where is this boundary cell? And the second, so it seems like all this Gabor filter, the simple cells that fit into this boundary cell have the same size receptor fields, right? And then just different orientations. Have you ever tried trying different sizes of filters?
Yeah. Okay. First question is, we don't know where boundary cells are or if they exist. Remember how we came at this? We said, let's say they do exist. How would they compute themselves based on cells that we kind of know are there? And so we would assume, the ingredients for doing this all exist in V1. So and also a boundary cell, if you just hit it with gratings and things, is going to look like a simple cell. It's going to be orientation tuned and location tuned and so on. So they could easily be mixed into the population. We don't know. So that's a critical thing to start, is to develop stimuli that can distinguish between simple cells and boundary cells, and we know how to do this. So that's point number one. Yes, and point number two is we've changed all kinds of things about the precursor cells, and the same basic story exists. There are the same types of interaction families exist. We have sort of monotonic excitatory things and monotonic inhibitory things, and then lots of non-monotonic interactions. So nothing fundamental changes if you make different assumptions about what the precursor cells are, their scale, their length, aspect ratio, anything like that. But it will change a little bit as it must, but it doesn't change the way that we would tell the story as far as we know. Yes.
How could you
test your model experimentally, either by recording neurons in V1 or by psychophysical experiments?
Well, so we're working with Jamie Mazer at University of Montana. We're trying to develop natural stimuli, structured natural stimulus sets to tease apart this exact issue. You know, it'd take a little while to talk about how to do that, but put it this way: a simple cell should be sensitive to kind of contrast. But a boundary cell should not care about contrast, to be sensitive to boundary probability, which is a very different thing. You can have a very high probability boundary that's low contrast, and you can have a high contrast thing that is a very low boundary probability. So they're dissociable, and so we can create stimuli that have all different combinations of all of those things and try to tease apart simple cells from boundary cells. And what we expect is we're not going to find categorical thing like, oh, these are perfect simple cells, these are perfect. We would expect to find some kind of a mushy spread like you do wherever you look in the brain about anything. Yes, you're on.
These non-monotonic responses imply that there might be some sensitivity to gain modulation in the inputs, because you might be, in some gain you might be in the monotonically increasing part, in another one you might be in the monotonically decreasing part, and so this could also mean that there's some sensitivity to contrast, although there are some forms of normalization in the cortex that might help. So is this a concern?
I don't get the concern. And by the way, these non-monotonic things are not, it's not non-monotonic activities, it's non-monotonic effect of increasing activity. So when the activity of the cell goes up gradually, its effect on its target can be excitatory and then later at a higher rate inhibitory. So it's not a non-monotonic activity rate.
From the start, the rate is higher, then you might be in the regime where it's going down.
Yeah. Well, yeah, but so this isn't a dynamical thing. It's just a statement of, at every level of activity of you, the presynaptic cell, what should your effect be on the postsynaptic guy? And that curve can be non-monotonic, which is unusual for the way we think about it. Lena?
So the performance curve you showed was interesting, but it seems like it's in the wrong shape if you wanted really good performance.
This?
And I'm wondering the recall thing.
This thing?
I'm not sure. Yeah, so if you want perfect performance here,
Well, what you'd ideally have, if you have a really good classifier, it goes up like this. And it goes really close to that upper right-hand corner.
do you have any intuition as to what aspects of this would make it go up on the right
Yes.
boundary?
Yes. We've worked, yes. Sort of a separate thing that we're doing is we've actually we've gone a lot farther. This is sort of the scientific thing, but we've actually worked on the engineering problem much, much harder, and sort of we're like up about here. But that's not really the point of this talk. But yes, no, that's a good question. What's missing? And
Well, I didn't know if it was a mismatch between, like, you chose these very canonical simple cells, and I don't quite understand what the inputs were in terms of...
it's a testament to is that boundary detection in natural images is extremely difficult. It is so, when you start going down into the pixels and you look there, I mean, I can't even put it into words. It is so messy that you just go, is it here or is it there? I mean, you just can't even tell what you're looking at practically when you look down in the pixel eyes. And you're asking a cell with a small receptive field or even a local little population to do a really good job. It's difficult. So it's hard to get up in that right-hand corner. You need a lot of hardware, much more than I showed you.
Does this answer Bruno's question?
What's his question?
Yeah. Is there, if you had 100, 10...
Well, okay. Actually, let me tie this to what Bruno. Bruno's pointing out the benefit of kind of exploding small numbers of cells into big numbers of cells to accrue benefits. Do you notice in that little network that I showed you that did the learning, we took each cell and we made like lots of copies of it with different properties. Yeah. This is V1 is also one of the kind of the gradual paradigm shifts over time has been that cells in V1 are very variable, and they have interest. Yves Fragnac has got papers showing all the variability in the receptive field properties. So we're kind of alluding to that and saying there's a lot of variability in there, and it just makes the learning much easier. So yes, it is an expansion recoding into variable units that makes the learning of this problem much easier. Reza?
So your original question wasn't whether there's a boundary here. Your original question was whether there's a fire hydrant. So now, like, if you take natural images and convolve them with the Gaussian kernel to a smooth boundaries out, you don't, psychophysically, you don't lose discrimination. You can still discriminate. So,
well, I disagree with what you just said. If you were to blur an image so there was no contours left, then you would not be able to...
Not so there's no contour left, but in a way that your cell makes a mistake. your cell can make a mistake and say there's no boundary, but a human can still realize, oh, that's the dog over there, the fire hydrant. Like an image is smoothed out a little bit, not to the point that they can take it down.
Well, okay, so the assertion that this would make a mistake and a human would not, well, this graph exactly quantifies that, because this is a very good, with human ground truth, this tells you exactly how well that thing is going to do, and it's certainly not anything close to perfect. I don't want to argue that the performance is great of this little network that I'm showing for as a demonstration thing. I just want to make the point that it's way above using one cell. It is all. You know, that I kind of cast it as a little bit of a paradox. Why would one simple cell is a really bad boundary detector? Okay, but then this is better, and so therefore there would be pressure for the cortex to discover or to take advantage of what it could take advantage of, which is to combine the inputs of many cells through these sort of local circuits that are learnable and do better. What is the brain trying to do? It's trying to do that.
We're kind of over time, so maybe we should take it to lunch and come back at 2. And thanks.